morning, everyone. First of all, I want to thank Debbie and Henry for giving me this opportunity to share my research with everybody here. So first, I want to check, can you guys see my screen well?
Yes, we can.
Awesome. Should I start?
Yes.
Okay, great. Well, as you may notice that the title of my talk today is a little bit different from what we listed in the program earlier that you may see, because I changed the title and some of the contents. Basically, I was trying to fit my talk today to fit in with our theme for the symposium, CCAT symposium. So basically, the talk that I'm going to give today is driving scenario modeling and simulation, a data-driven method. So if you have questions, feel free to type in your questions in the question sections, and I can get to it later on. So before my talk today, I would like to give you some background, as some of you may already very familiar with this figure. So this is the SAE definition for the advanced driving systems from level 0 to level 5. So basically level 0, you don't have any assisting systems in your car. It's just a traditional legacy car. So some people may ask the question, if I have the cruise control, would that count? So basically, the answer is not really. So it still counts at level 0. However, if your car does have the adaptive cruise control system, so then congratulations, you're moving on, moving forward from level 0 to level 1 system, which is called a driver assistance system. So basically, for this level, vehicle is controlled by the driver. But some driving assisting features like adapt cruise control or lateral control assist, lane keeping assist, the features available to help you from one of the directions. So if your car has more than one, like two driving features, assisting features, like you have both ACC, adapt cruise control, and lane keeping assistance systems, which is the current most available popular in market system. We call the level 2 partial automation. So the vehicle has combined automated functions, like you have both ACC and a lane keeping system. Then moving forward with the level 3, it's called a conditional automation system. So basically, for level 2 and level 1, the drivers still need to monitor the driving environment. Their hands, and most of the time, their hands are required on the steering wheel, and they need to check for the traffic conflicts. However, move forward to the level 3 conditional automation. So under certain conditions, so the drivers do not need to put their hands on the steering wheel anymore. Right now, we have some system called level 2.5 that the drivers can hands off, but for a lot of the level 2 system is still there. The driver's hands still are required on the steering wheel. So the trick thing about level 3 is basically under certain conditions, you can just go off the driving task. However, because of the limitations of the sensor and all kinds of control algorithms, so under certain conditions that the car still cannot handle some complicated scenarios. So then the drivers need to retake over the driving control. So that's the level 3 called the conditional automation levels. So then you move forward to level 4 and level 5. For those systems, you don't need to hand the steering wheel anymore. So there will be no steering wheels in your car, and the drivers basically just enjoying the other tasks. They can making phone calls, working on emails. They can basically watch videos, And so that is the end. And as the transportation engineer, that is the ideal land we want to land to. So here's a list of the lead OEMs and companies, IT companies that who have claimed that they are working towards the self-driving cars, and a lot of them already shared the roadmaps going to the level 4 and level 5. So having said that, the question we want to ask ourselves is basically, are we there yet? So I'm sharing the two pictures, which is actually the two pictures are 50 years away from each other. The figure on the left is basically 50 years ago. What's our dream or our imagination of autonomous car, right? While the figure on the right-hand side is just showing today what's our imagination, what our picturing, what the passengers should be doing in the autonomous vehicle. Obviously, for both cases, they share a lot of great similarities. So people are not engaging the driving task. They are doing whatever they want to do and just enjoying the ride. So while we are sharing a great similarities from 50 years ago, and today we made a big progress in the autonomous vehicle technology development. So then the next question we want to ask is that, are we there yet? Of course we're not, right? So why we are not there yet? So there are a lot of factors and reasons. So one of the reasons is basically autonomous systems are complicated and they are expensive. For example, the sensor technologies, each of those sensor technologies, they all have limitations, and they basically can be impacted by environment and weather. For example, the video camera based on the sensor, so they have limitations that if the road marking is basically blocked by the snow, or the road marking is weared off. So then the sensor technologies, the video camera just cannot work appropriately to make sure the car is driving within its defined driving lane. And also we know that radar system, right? It also has limitations. It basically has limitations in detecting small objects as well as stationary objects. So we're also facing a lot of problems like a sensor fusion, and software and hardware need to be linked. And also we have 100% market penetration. It will take a long time that we have 100% market penetration. And of course, we are developing this technology from scratch, right? So not all the safety situations can be determined or predicted. So the greatest motivation of introducing self-driving cars is basically we want a safer road, a safer transportation system. While at the same time, when we introduce those technologies, also there is some situations that we have never tested and considered. So those is also one of the challenges for us to face in the future development. The second big part is that the users are still naive. So many old vehicles still be on the road for quite some time. And even for people working on this domain, they still have limited of knowledge of understanding what other OEMs, what other people are doing. For example, one of the examples is that the adaptive cruise control system. The same system, actually, if you look at different car models across different OEMs, you will find that different OEMs will have different names for the same ACC systems. So as the user, the drivers, the commentary drivers, they do not have those background professional knowledge of all those terminologies. So users are generally still very naive about those technologies. When you call those, some of them even cannot tell the differences between autonomous vehicle and automated vehicle. So basically, there is also concerns of user acceptance. Some users attempt to adopting to the new technology faster, while some users are more hesitating in adapting to the new technologies. So those are still also the challenges and the things we need to consider. And the other thing is that our road and infrastructure systems are not ready for this, the large deployment of the system. One of the examples is that our road systems may have a lot of pit holes, and the lane marking systems are not that perfect for the video system to detect, right? So having said that, we have all those challenges. So when we introduce, every time when we choose a new generation of the AV technologies, so we need to test. We need to basically test across different scenarios to make sure the safety is under covered. So, but every time when you introduce a new technology, you cannot just keep testing on the real road, because one of the simple reasons is it's relatively expensive to test every single step. So then one of the possible solutions is that we can develop those scenarios in a virtual environment. And then we can test those AV control algorithms and in the virtual environment, and then we can tune the vehicle control algorithms accordingly. So today I will talk of my work in this domain. It's basically a data-driven method to modeling and to model and simulate the corner cases of driving scenarios. So basically, here's the figure steps. What we did is that we start with the real world driving data. Then we generate a computational and machine learning based algorithms to basically predict the vehicle behavior. So then we use that kind of algorithms. Then we're gonna simulate all the interactions of the vehicle under that scenario with other road users. So today I will be talking about two studies. The first one is that how we use naturalistic driving study to, and the deep learning method to model the car overtaking behavior. So part of these results we have presented in the Transportation Research Board meeting earlier this year, January. So background, why we want to do car overtaking truck behavior modeling. What simple answer is that overtaking, relatively speaking, is one of the most complex driving maneuvers that to be modeled. And the car models are mostly focusing on car overtaking. However, we understand that a car overtaking truck is more complicated considering the larger size of the truck. So that is the motivation. We want to use the deep learning method to model the car overtaking truck behavior by using naturalistic driving study data. So there are three main objectives of this part of the work. The first one is that we want to develop a driving style estimation algorithms during overtaking maneuver. So why we want to do that? So when we research the literature work, so most of the current work on the car overtaking behavior is centered on a generic model by considering driver as a whole group of population. However, we also understand that there is a huge variance among drivers. Different drivers have different driving styles. For example, some aggressive drivers drive totally different from very conservative drivers. So we want to, by building these driving style classification in the overtaking model generation. So the second objective of this study is we want to compare and select the best deep learning model that alleviate basically coping with the time shifts. And then the third objective is that we want to validate those models by incorporating driving styles. With that model will have a better performance compared to the generic model when considering driver as a whole group. So these figure on the right-hand side is basically to show you a layout of our methodology. First of all, we basically use the clustering methods to divide the drivers into different groups based on their own driving styles. So we use a set of the vehicle kinematic features as the model input. So then the drivers basically will be classified or tagged or labeled into different groups. So then we use the deep learning methods by modeling when the car is performing overtaking truck behavior, and also considering the different driving styles. Can we develop a relatively accurate model to predict this type of behavior? So the data we used is actually from the Amtree naturalistic driving study. It's called a Safety Pilot Model Deployment Database. So that is one of the largest connected vehicle FOT field operational tests that led and conducted by Amtree. So at the peak time, we had around 2,800 vehicles, including personal vehicles, passenger vehicles, trucks, and buses. So we have more than 35 million miles of hour of driving already. And among those 2,800 vehicles that participate in this study, about 140 vehicles we say fully equipped. That means that those 140 vehicles were equipped with mobile eye sensor, which can detect the objects in front of the vehicle. That include trucks, cars, SUVs, even pedestrians and bicyclists, as well as the DAS, data acquisition system. So all the vehicles are hundreds of data channel recording the vehicle kinematic speed, acceleration, yaw rate, as well as different views of the video, the front view, as well as the driver view. So this is one of the example of the car overtaking truck events that are captured in the safety pilot data sets. As you can see, basically we have the front view to tell what's going on in the scenario with the during the overtaking event. And this is basically to show you what in the SPMD study, what the participants' vehicle have traveled to. And this is basically a speed distribution of those 140 fully equipped vehicles. So methods. So the data we used, as I introduced earlier, is from the safety pilot study. So then we went to the database basically by using the keywords that the mobile eye sensor flagged there is a truck in front of the car, and we also used our own algorithm definition by defining the car overtaking as well as the car lane changing behavior from the database. So by using all the criteria, we have identified two types of car overtaking truck events. So as you can see from the figure in the middle here, so basically the one type is the typical overtaking behavior. So a passenger car was driving behind the truck and earlier. So then basically the car was prepared a lane changing to overtaking the truck, then come back to the original lane. So that's type one. The second type is we included that just as a comparison. So in this type of event, so the drivers, passenger car drivers made a lane change and surpassed the truck, but didn't return back to the original lane. So by having this definition, totally we have about 805 valid events we identified on the highway from the SPMD database. And the algorithm we used is basically, first of all, we used the k-means clustering methods to classify the different driving styles, and we use the Gaussian mix distributions basically to map with each of the driver group. Then later on, we used combined empirical mode decomposition with LSTM, stands for the long short-term memory methods, is one of the deep learning, commonly used deep learning methods in this type of vehicle modeling. And so followed by that, we for each of the overtaking event, we basically extracted a lot of vehicle kinematics and dynamics, including the speed and overtaking speed, and also the lateral movement, as well as the longitudinal movement. So what we did is basically we introduced the time shift to measure the time lag between the predicted and target values. So when you're generating the prediction models, you have different time prediction, time consideration. You can predict based on your 1 second ahead of you based on your current vehicle status, or you can basically predict 1.5 seconds ahead of the current vehicle status. So in this study, we have used the different time shifts in our prediction model to identify what is the threshold time threshold that based on the current algorithm and current input variable, we can identify a relatively optimize the prediction model. And also basically the deep learning method that decompose the dependent variables into different components that we can, I will introduce you in the later slides. So one of the results is that the first step in this algorithm is we used k-means clustering as well as the Gaussian mixture distribution to categorize and estimate the individual driving styles. So basically by using k-means clustering, we have identified 2 groups of drivers. For these 2 groups, we call it one of is relatively aggressive, featured with more speeding behavior, more hard braking behavior, following closer. And the other group, we call it a relatively conservative group. Comparatively, they have much less speeding behavior, as well as less frequent hard braking behavior. So as you can see from this figure here. So then we basically first we use the k-means to classify all the driving events. So eventually we are interested in labeling drivers. So the drivers, then basically we use the Gaussian mixture distribution to identify the threshold to for the number of aggressive events and the number of conservative events, to basically label each of the driver, whether they should fall into a relatively conservative group, a moderate group, or risky driver group. So then based on the results, so all the drivers were divided into 3 groups. One is conservative, moderate, and risky driving. So the second step, the first step is basically we classify all the overtaking events. Then we basically label each driver based on the threshold of how many risky events this individual has. So then the second step is basically we want to develop a prediction model to understand and to predict whether, based on the current vehicle dynamics, can we predict whether the vehicle is going to make lane changing and overtaking behavior, yes or no, as well as its longitudinal and lateral control variables. So we have 2 types of model outputs. One is binary, so whether the drivers is going to make overtaking, yes or no, the second type of model output is a time series output. Is basically the next time point of the vehicle speed, acceleration, and movement. So there we use the EMD LSTM. So basically to find to try the different lead time, like 0.5 seconds, 1 second, and 1.5 seconds. So as you can see that our methods actually has produced a pretty good results so far. And the figure on the right corner here, as you can see, the R square of the prediction when you use the EMD LSTM method is relatively high compared to other type of machine learning method like a support vector machine. So the results gives pretty accurate predictions. And also the next step is that when we incorporate the driving styles in the model, whether that gonna improve our model accuracy, yes or no. So as you can see from both the figures here, that once we incorporate the driving models from here, the right figure here, you can look from the I-squared value. When we included the driving styles in the model consideration, the model accuracy is actually greatly increased when compared to no driving style is considered. So basically, the message here is that our methods of using EMD LSTM can give us a relative accurate model prediction. And also the lead time, the model accuracy, actually the performance decreases with the lead time, which is understandable. And the further, if we include individual driving styles in the model consideration, the model performance can also be significantly improved. So the message here is that by using data-driven methods and the deep learning method, we are able to develop relatively reliable and accurate prediction models to predict vehicle dynamics. And so then the next question we want to ask is that once we have those models generated, how we should move forward with the next step. So that is the next study I want to introduce. And the one thing I want to basically to mention here before I talk about the second study here is that for this part of work that my interest is all the road users, including vehicle, all the vehicles, as well as vulnerable road users. So when we develop the AV technologies, their interaction with vulnerable road users is very critical, because that is a very challenging part, because currently a lot of sensors that they have a limitation in detecting the small objects like pedestrians or even bicyclists. So by basically how we can utilize these data-driven methods to identify challenging cases for the interaction of the vehicle with other road users is also one of the other big interests of this part of topic. So for this part of analysis, I will share some of, because this is ongoing, I will share some of the status and the results based on our current findings. So we are interested that when the vehicle, the AV implemented on the road, how they should be designed, right, to interact with pedestrians, especially considering pedestrian safety is becoming a rising problem to the society. If you look at the NHTSA figure, the fatal crash figure, not just fatal, or the crash fatality of the pedestrians, you can see, generally speaking, all other traffic deaths, fatalities, there is a trend of going down, thanks to our all the advanced driving assisting systems and all other factors and contributions. However, there is one contradictory observation is that when all the other deaths is going down, but the fatality of the pedestrian is going up in recent years. So that is really of one concern to us. So we are really want to tackle this problem and understand how the AV should be designed to better address these issues. So based on the crash data analysis we did, that we have identified pedestrian crashes mostly occurred in urban area. So that is pretty under your expectation. And the pedestrian crashes are most common during dark time than compared in the daytime. And also weekday crashes are mostly between 6 to 9 p.m. And the weekend crashes even occur later, because the weekend we have more pedestrians on the road during later of the night. And for pedestrian crashes, they are slightly more likely on weekends than weekdays. And the majority of the crashes are non-intersection related. Actually, we have identified that jaywalking, mid-block jaywalking is one of the leading crash scenario for pedestrian fatalities, as you can imagine, due to the greater speed, traveling speed of the vehicle. So for this part of work, that what we did is that we look at also we look at the safety pilot study data to extract all the pedestrian related events. So we have identified a set of we call it corner cases, which is the challenge scenarios when a vehicle interacting with pedestrians. So that can be challenging to human drivers, and they can also be challenging for AVs. So one of the scenario I'm showing here is that, as you can see, when the vehicle is driving, so there is pedestrian crossing the road. So there is a crosswalk. There is a crosswalk nearby the pedestrian. However, due to the road surface color and also the pedestrian, what the pedestrian wearing, it's pretty challenging for the human drivers, the eyes, to distinguish the pedestrian until far ahead. But that can be solved by a better sensing technology of the AVs. So, but we are interested in this scenario. So what is the typical speed profiles, approaching strategies should be designed and recommended for the AV technologies. So the other challenging part, as I mentioned, this is one of the most dangerous scenario for the pedestrians is the jaywalking. So, so here's another example that the pedestrian is crossing the road without using the crosswalks. So this can be pretty challenging for both human drivers as well as AVs. So those are just different examples of the jaywalking scenarios. And also there's other scenarios that we have identified, like pedestrians is walking or running on the road sides. So without designated walking bike lanes or pedestrian walk sides. So this is another example that the vehicle does not react to the pedestrian on the sidewalks and continues to travel in a constant speed. So just want to show you the video one more time. So we have identified the other challenges that we have found, that basically when there is a road construction in the median, and the pedestrians, like the workers, can be blocked by the view. So this can be, challenging for both human drivers as well as the sensor technologies. So we are interested on those scenarios, how the AV should be designed and addressed. So this is another example. We have found that as we mentioned, when we go through from level 0, level 1, level 2, level 3, level 4, even 5, and especially between level 2 and level 3. So the sensor technology rapidly developed, but still there is a lot of limitations. So here's one of the example that we have observed that on certain side of the road that the mobile eye keeps flagging there is a pedestrian. But when we checked the video, that there is no pedestrian for that cases. So then basically we drove our researchers drove to the site and to identify what's really going on. Then we found that there is a mailbox in that area that keeps flagging to the video sensor saying there is a pedestrian, but actually in the reality, this is not. So this is also something that we are interested of how the sensor works and how those different unrecognized the false alarms should be addressed as well. So as this is a current ongoing work, once we identified all those interesting scenarios, and we are interested in basically generating and model all the vehicle control algorithms into the virtual world. So then the newly developed ADAS systems can be tested in the virtual settings with relatively much lower cost and also more timely fashion. So here I just want to give you one example of what we have simulated about one pedestrian jaywalking in the snow-covered neighborhood that our participant drivers are driving in the neighborhood. It was a winter day. Then the pedestrian was walking, not using the crosswalks. And this is not really challenging, but I just want to demonstrate to you how we are basically simulating the real world cases in the using the software in the virtual environment. So this is one of the scenario to representing what you just saw from the naturalist real world driving data that the pedestrian was doing the jaywalking. So one of the, as we are still exploring different software features and capabilities, one of the challenges that we understand that it is pretty challenging to simulate certain conditions in the software, like the snow covered roadside. So then basically we need to change the vehicle control algorithms. So, and so that is what I want to share today. And of course, the second part of the study is still ongoing, and hopefully we can have more solid results to report to you next time. So I also want to extend our appreciation to our sponsors, CCAT, and MCD and Toyota Research Institute and State Farm. They joined support all my students that their names are listed here who actually have done all the work. So basically today I'm just repeating what they have done. And that's it. And thank you all for being here today. I do see there are some questions. So.
Yep. Let's see. First question was, have you looked into motorcycle involved crashes similar to your look into pedestrian involved crashes? If so, what have you found?
Oh, thank you. That's a very interesting, that is a very interesting question. Yes, we were interested in the motorcycle involved crashes. However, we want to do step by step because as you can see, the pedestrian crashes of fatality is becoming more of an issue. So that's why we started with pedestrian and bicyclists. Then later on, we'll get to motorcycle related crashes. So yeah, so basically to answer your question, we have not done that part yet, but in the future we will. Thank you, Dan, for the question.
Second one from Sue Chrysler.
Yeah.
On the driving style classification work, how big were the training and model fit data sets?
Oh, so Sue, very good question. So for the training part, we basically just follow 7-2-3. So we basically split the data 10 folds, then 7 for training, 3 for validation. And the model fit data, yeah. So I think that I answered your question for that part.
Sue says yes, thanks. From Paul Rao.
Thank you, Sue, for the question.
What other driver styles may be discovered by other means than the classes of aggressive, conservative risk takers?
That's a very good question. So basically, based on the data that we have, and also the algorithm suggests that all the drivers can be labeled or classified into 3 groups: conservative group, conservative drivers, moderate drivers, and aggressive drivers. So this is based on, generally speaking, how they typically drive and in a relatively long time fashion. So I think that's basically is a statistical way to look at the driving styles. So if you are talking about whether some drivers will be leave out from those 3 categories, oh yeah, So Paul asked a follow-up question, is the older versus novice drivers. So that's a very good question. So actually for that part, we are also working on the further classification of the driver characteristics in each of the driver aggressiveness levels. So basically, the fortunate that at Umtree we have quite a rich data sets from the novice driver, which is that from the teen IBBS study that we conducted 10 years ago. We had a 40 teenager who were novice driver, like second level 2 Michigan driver license, 16 years old back that time. So they just newly received their driver license. Then we also have the other data sets of adult drivers. We have middle-aged, younger part, 20 to 30 years old, middle-aged, 40 to 50 years old, and older drivers, basically 60 to 70 years old. So there, when we have the classification work done, we basically put all them together to look at which group has more novice driver representative, which group has more older driver. As you could imagine, the results show that the aggressive drivers has more teen and younger drivers, while the conservative driver group is mostly older drivers. So I think I answered your question, right, Paul?
So I have one question, if you don't mind. I was wondering, about the pedestrian crashes being, most of them are non-intersection, and you had mentioned that's because most of them occur at mid-block. And so I was wondering if any of your data suggested that the mid-block crosswalks that we have in Ann Arbor were helping to alleviate that problem, or is it just subdividing it into accidents between the intersection and the mid-block crosswalk? And I don't know if you'd have enough data to look at that, but I was just wondering.
Well, that's a very good suggestion, Debbie. We have not looked at particularly Ann Arbor data, but maybe that's a good way to for us to look at the data later on. So currently, we're just looking at all the United States crash, especially the fatality crash data, to look at what is the typical crash scenario for pedestrians. Then we identified that the middle block is the one of the leading scenario, but that's a very good suggestion. Maybe we should look at how the Ann Arbor cases, and especially with the new smart intersection technology, the project that recently Henry got. So hopefully we can identify a pattern, compare before versus later.
Sure.
But that's a very good suggestion. Thank you.